This next video covers matched pairs T procedures. So comparative studies are more convincing than single sample investigations. And for that reason, one sample inference is less confident than comparative inference. So study designs that involve making two observations on the same individual or one observation of each of two similar individuals give us paired data. And when paired data results from measuring the same quantitative variable twice, as in the job satisfaction study, we can make comparisons by analyzing the differences in each pair. And if the conditions of inference are met, we can use a one sample T procedures to perform inference about the mean difference. So, to compare the response to two treatments in a matched pairs design, you want to find the difference between the responses in each pair and apply the one sample T procedures to these differences. So of course, we're going to go through an example and then talk about some robustness of T procedures. So, will chimpanzees recruit another chimp when solving a problem that requires collaboration? So the same 8 chimps were faced with two versions of a problem, one requiring collaboration with another chimpanzee to solve, the other not requiring such collaboration. So the table shows how often in 24 trials of each version of the problem, each chimp opened a door to request collaboration. So chimp 1, 16 collaborations, 0 no collaborations. So we found the difference in the number of times they collaborated. So is there evidence that chimpanzees recruit partners more often when a problem requires collaboration? Oh, okay, cool. So there was a test that required collaboration, and there was a test that required no collaboration. And this is the number of times they opened a door to request collaboration. So chimp 1, on the test that required collaboration, asked for help 16 times, but on the one that didn't, he never asked for help. Chimp 8, when he did the 24 collaboration test, always asked for collaboration. And even when he didn't, he asked for collaboration 20 times, okay? So is there evidence that chimpanzees recruit partners more often when a problem requires collaboration? So we plan to take mu to be the mean difference. That's going to be this right here. Then we calculate our mean x bar. We need to find x bar. And the number of times a partner was requested. The null says the need for collaboration has no effect, right? And the alternate hypothesis says that partners are recruited more often when a problem requires collaboration. So we stated our problem, now we need to plan. So our plan is to test the hypotheses that mu equals 0, so the difference will be 0, there's no difference, and ours say there is a greater difference. So we can make a stem plot, right? And according to information from the researchers, we may regard the chimps as a simple random sample for their species. The stem plot looks left skewed, but the corresponding dot plot shows that the stem plot is mismeaning and there's no major signs of non-normality. It is a little skewed to the left, but not so bad. And it's hard to judge normality from 8 points. This is 8 points. And that's why we have student T's, right? So we can use them on samples less than 30. So the 8 data points have a mean of 12.375 and a sample standard deviation of 4.749. So our test statistic T is x bar minus 0, that's our mu naught, that's this, mu naught, over our sample standard deviation over the square root of n. So I get 12.37 minus 0 over 4.749 over the square root of n equals 7.37. And then we need to go to our z table. So For a t distribution with 7 degrees of freedom, this t has an upper tail probability of 0.000077. That's small. So we can reject our null hypothesis. Because of the very small p-value, we reject our null hypothesis, we don't accept, but saying our all null hypothesis could be true at a confidence level, and deciding that chimps request collaboration more often on average when required. So lastly, let's talk about the robustness of T procedures. So a confidence interval or significance test is called robust if the confidence level or p-value does not change very much when the conditions for use of the procedure are violated. So when we're using the T procedure, except in the case of really small samples, the condition that the data must be a simple random sample from the population of interest is more important than the condition that the population distribution must be normal. So it's more important that it's a simple random sample than that from the sample it comes from be normal. If sample size is less than 15, you're going to have to use a T procedure. If the data appears close to normal, use a T procedure for sample sizes less than 15. If the data are really skewed or they're outliers, don't use T. It's not going to be reliable. If you have a sample size of at least 15, T procedures can be used. So like at least 15, it could be greater than 15, greater than or equal to 15. Then we can use it unless there's outliers or strong skewness. Again, outliers ruin everything. And when there are large samples, our T procedures can be used even for clearly skewed distributions when the sample is large, roughly in greater than or equal to 40. Other textbooks say 30. But this one refers to it as greater than 40. Now, what do we do if our data is clearly not normal? Well, if lack of normality is due to outliers, and you'll see this in statistical studies, right, it may be legitimate to remove outliers, right, if they're really skewing your data. But if an outlier appears to be real data, you really shouldn't arbitrarily remove it. When you're doing a write-up of your data, if you do remove an outlier, you should definitely make note of it. In some settings, other standard distributions replace the normal distribution as models. Statistical studies in these areas use families of right-skewed distributions rather than normal distributions. There are inference procedures for the parameters of these distributions that replace T procedures, but I'm really not going to cover those in this course. That's maybe like a higher level or graduate level even stats course. Next, there are modern like bootstrap methods and permutation tests, which use heavy computing to avoid requiring normality. Again, we aren't going to cover those in this class. And lastly, there are non-parametric methods, which do not assume any form of the distribution of the population. And common parametric methods do not make use of actual values of the observation. This is some not this class stuff, but there are ways to deal with non-normal data.